Hybridization in organic compounds. The simplest of organic compounds, namely hydrocarbons, are classified as alkanes, alkenes, and alkynes. Consider ethane, ethene, and ethyne as their respective examples. The ethane molecule is ditetrahedral and has a bond angle of 109 degrees 28 minutes. Ethene is a planar molecule with a bond angle of 120 degrees, while ethyne is a linear molecule with a bond angle of 180 degrees. All these three hydrocarbons differ from each other in geometry and bond angle. Can you explain the reason behind this difference? Well, the concept of hybridization clarifies this difference quite satisfactorily. In this topic, we will focus on the three different types of hybridization of carbon atoms: sp3, sp2, and sp. Let us start with sp3 hybridization of carbon and alkanes, taking ethane as an example. There are 2 carbon atoms and 6 hydrogen atoms joined by single bonds in this molecule. The orbital picture of ethane looks like this. We can thus visualize 7 internuclear axes between them. A chemical bond formed by orbital overlap along the internuclear axis is a sigma bond. Thus, both the carbon atoms are surrounded by 3 carbon-hydrogen sigma bonds and 1 carbon-carbon sigma bond. These bonds are directed along the corners of a regular tetrahedron, and all carbon-hydrogen bonds are of the same bond length. Let us now remove the 6 hydrogen atoms from this structure. Also, drag the 2 carbon atoms apart. We can clearly see 4 equivalent sp3 hybrid orbitals of each carbon atom. Each of these orbitals has 1 lobe bigger than the other and is occupied by a single unpaired electron. Let us find out how the concept of hybridization explains this structure of ethane. For this, consider a carbon atom in the ground state. Its electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz0. On excitation, an electron jumps from the 2s orbital to the vacant 2pz orbital, resulting in an electronic configuration of 1s2, 2s1, 2px1, 2py1, 2pz1. In the next step, the 2s, the 2px, the 2py, and 2pz orbitals of this atom intermix. This process of intermixing of atomic orbitals is called hybridization. As a result, 4 equivalent orbitals called sp3 hybrid orbitals, directed along the 4 corners of a regular tetrahedron, are formed. When 2 such sp3 hybridized carbon atoms approach each other along the internuclear axis and overlap, a carbon-carbon sigma bond with a bond length of 1.54 angstrom is formed. 6 hydrogen atoms now approach and overlap the remaining 6 sp3 hybrid orbitals of both the carbon atoms, forming sigma bonds with bond length of 1.09 angstrom. Note that whenever a carbon atom in an organic compound forms 4 sigma bonds, which are directed along the corners of a regular tetrahedron, it is sp3 hybridized. Besides sp3 hybridization, the excited carbon atom may also undergo sp2 or sp hybridization. In sp2 hybridization, 1 2s and 2 of the 2p orbitals intermix. Consequently, this hybridization is termed as sp2 hybridization. The hybridization leads to the formation of 3 equianergic sp2 hybrid orbitals. As you can see, each sp2 hybrid orbital is also bilobed, one lobe bigger than the other. But the 3 orbitals are directed along the 3 corners of an equilateral triangle. The half-filled p orbital, which was not involved in hybridization, lies at right angles to the plane of the equilateral triangle. This hybridized state results in a double bond. Imagine a similar sp2 hybridized carbon atom approaching this carbon atom. As these atoms come closer, an orbital overlap takes place along the internuclear axis, forming a sigma bond. At this stage, the unhybridized p orbitals, which lie above and below the plane of the sigma bond, also come very close to each other and overlap laterally, resulting in the formation of a pi bond between the 2 carbon atoms. Thus, there exists 1 sigma and 1 pi bond between the 2 carbon atoms. The other 2 valencies of each of the carbon atoms are satisfied by 4 1s orbitals of hydrogen, hence forming an ethene molecule. Thus, a doubly bonded carbon atom involves sp2 hybridization. Another process of intermixing is called sp hybridization. This involves the mixing of 1s and 1p orbital of an excited carbon atom and results in the formation of 2 sp hybrid orbitals. Now, imagine another sp hybridized carbon atom approaching this carbon atom such that the sp hybrid orbitals of the 2 carbon atoms face each other. These orbitals overlap along the internuclear axis, resulting in a sigma bond. Each of the carbon atoms also have 2 unhybridized p orbitals, namely the py and pz orbitals. These orbitals, which lie in 2 mutually perpendicular planes containing the sigma bond axis, also come very close to each other and overlap laterally, resulting in the formation of 2 pi bonds between the 2 carbon atoms. The 4th valency of each of the carbon atoms is satisfied by 2 1s orbitals of hydrogen, which also make sigma bonds along the internuclear axis, and an acetylene molecule is formed. A carbon atom with a triple bond is thus sp hybridized. To summarize, we have studied that whenever a carbon atom in an organic compound forms 4 sigma bonds directed along the corners of a regular tetrahedron, it is sp3 hybridized. A carbon atom that forms 3 sigma and a pi bond is sp2 hybridized, while the one in which it forms 2 sigma and 2 pi bonds is sp hybridized.